Octavio?
Yes, Michele, wait a second.
Yeah, just to check everything is okay.
Yeah, the projector is not working. I'm going down just to check what's happening.
Okay. Did you turn on with a key?
Done. I fixed it.
Okay.
I will wait until 5:35 and then I will start.
Okay. I think the recording is working.
Yeah, I logged in from with your account on the PC.
Okay, cool.
Okay, so I think I'll start also because we only have 2 hours. So just before, oh, let me turn on my camera. So can everybody hear me, by the way, online?
Yes.
Okay, good. So I sent an announcement today with the new version of the code with the fixed problem. As I mentioned, I was using the wrong dimension as your colleague as your colleague pointed out. Probably when you were trying to pull, if you tried to pull directly, you got a message saying that you needed to commit your changes or something like that. In any case, if you manage to reach to the point at which we were yesterday, then you're fine. If you didn't manage and you just want to get rid of all of what you did and just start from where we were, what you need to do, it's this. So you do git reset -- hard, And this will basically remove all of the changes that you did. And it will point you to the previous state in which you were. So if you do this, it says where is your head. So this means where the state in which you are. And then from here you can do git pull origin lav tree, and then this will get all the changes that I just pushed this morning. And of course I already have them, so here they are. Okay, so before I wanted to give a bit of explanation about the trajectory that we worked out yesterday for the joint, the fifth order polynomial trajectory. So let me share my screen. Okay, here. Okay. So, okay, you can see my screen now, right? Okay, good. Let me make it larger. Okay. So let me move this. I can move it. Yes. So these are the equations for the fifth order polynomial. It's called a fifth order polynomial, of course, because t, the time, it's to the power of 5. But then we take the derivative, the first derivative, which will give us the velocity of the joint. And then we take the second derivative, which will give us the acceleration of the joint. So we know that for time equals 0, that our equations reduce to this. And actually we know what all of these are at q times 0, which are basically so our initial states. And if we're starting from not moving, from a state of zero motion, then our acceleration and our velocity, it's also 0. So we know all of these 3 values. Then these are the equations for time equals TF. So TF, it's basically a value that we just defined, which says how fast we want to move from one point to the other. So the time that it's going to take from one point to the other. When I mean point, it's any kind of trajectory. So in this case, it's from let's say a circular trajectory, but it can be any type of trajectory. And these are the equations, which is just basically this, substituting TF, which is the final time. And actually, we know QTF from our solution of the inverse kinematics, because if we're trying to look at for a point and we want to move to that point, we get the joint positions at that point using our inverse kinematics, and then we can work out these equations. So in the end, we have 3 equations for the initial states and 3 equations for the final states. So we can actually find the coefficients of this A0, A1, A2, A3, A4, A5, which are 6 AI coefficients. And that's how we solve them. You can solve this with any method you want. Of course, the most computationally efficient for a computer, it's using a matrix. So you express A0, A1, A2 as a vector. And then the rest is what's on the right side becomes a matrix times a vector, and what's on the left side becomes a vector. And then that's how we got to these equations. So let me then go back to the code, to the point where we were yesterday. So, okay. So yesterday we left off at the numerical inverse kinematics. Okay. So let me comment this first. So we implemented basically, I'm not here. Let me get the slides. Okay, so we implemented this algorithm. Also might want to get the description. Give me 1 second. Not this one, but this one. Okay. So we implemented this algorithm without the step reduction, and we found that it solves the problem. But so where we here? Okay. Okay, we are here. Okay, let me comment this out. Okay, so it solves this problem, let's say, because this is within the reachable space, and then this is a good initialization. So if we run our kinematics file, then we'll see this. The robot is able to reach to the position, and it gets to the point. Now, if we take a look at our, so here I'm printing the inverse kinematics, the number of iterations that the inverse kinematics took to solve. So remember that it's a recursive method. So it took 18 iterations. Now I'm showing the point that we selected, which is the minus 0.5, minus 0.2, 0.5, and pi over 3. And then the solution, it's very close, and I'm plotting the norm of the error. So the point minus the inverse kinematic solution, and it's basically 0. And then these are the positions that the inverse kinematics algorithm is showing. Now, an interesting, now let's implement it with the variable time step, the line search algorithm. Okay, so to do that, let's give a look at the algorithm itself. So here we have it. So we basically, from this point, we jump directly to the output. So from the update step, we're jumping directly to the output step. What we want to do is actually verify let's say have a better alpha in case your initial alpha is bad. So so the first part of the algorithm, it's basically the same. So we're first computing. So the first step is to compute J transpose times J inverse, and this is J transpose times J. So first we have, well, we compute the geometric Jacobian, we compute the direct kinematics. Once we have the geometric Jacobian and the direct kinematics, we use those two to compute the transformation from the geometric Jacobian to the analytic Jacobian. And we then compute we get the force sphere rows, because we want that our task space is X, Y, Z position and roll orientation of our end effector. So these are the four, and then we compute again J transpose J. Then we take the inverse of that, multiply it by J again. So this is our pseudo inverse. Then so the Newton step, the delta Q, reduces to this. So delta Q, it's equal to our initialization times our alpha, and then we say Q0, then we update Q0 to Q1, and then we do the iteration again. Okay, so let's look at what's next here. Oh, what did I do? Okay. Okay, here. Okay. Wanna uncomment this? Uncomment the one on top. The font, is it too small? Okay, let me try that. I'm gonna make the font a bit larger. Font here. So is that okay? 24. Is this fine? Good. Okay. So yes, so we reached this point in our preview. So this is our update step. So if we look back at our flow chart, we have we're at this point. Now what we need to do is to compute the error at the next step, right? So you do a test with your current estimation of the inverse kinematics, and so those are your values of your joint positions, and check what the error is there. So to do that, we basically have to repeat the process that we did before, but now instead of using Q0 here, we're using Q1. So we test the direct kinematics here. So maybe I can type it along with you. So okay, want to change to English. Okay, so T underscore this. So basically what I'm doing here, it's solving the direct kinematics. So we have this direct kinematics function, and I'm just taking the transformation from let me close the door. Okay, so I'm taking here the direct kinematics of the end effector, replacing our value of Q0. So this is just giving me the position in X, Y, Z space and the orientation. Then I take the rightmost three elements on the homogeneous transformation matrix. Then here I'm obtaining the rotation matrix. Then I'm getting the roll pitch yaw angles of that one. Then I'm just interested in roll because our task space is X, Y, Z and roll. And then this is the important part. The previous part was just doing the same as we did before. And the different part is that now we're taking the error of the position of the end effector that we want to reach minus the position of the end effector that we computed here. And then what we're going to do is that we're going to compute the errors. So we're going to compare the error. So this is the error that we just computed. E bar 1 is the error of our first test, and E bar is the previous error. Okay, so we're going to compare them, and then if we look back at our algorithm, this is basically this part, and you have alpha times gamma times alpha times your error, your current error, which is basically this. Gamma, in our case, the gamma that I chose is 1, and the beta that I'm choosing is 0.5. Remember that these values are between 0 and 1. Basically here, I'm just forcing it to be basically the error the same. So if you want to be more conservative, basically what you're saying in this step, it's like if my error is equal to the, it means that, so if this error is larger than the actual error, this means that I'm very far. So which is sorry, the other way around. It means that I'm getting close enough to it. So if it's the opposite, then I need to reduce my step, because then I'm taking too large steps and my error is just it's not reducing fast enough. So yes, here. So this is basically what this step is doing. So the threshold is gamma times alpha times our the norm of the error. And then I'm just doing this comparison here and just implementing this step here, the step reduction here. And I am printing alpha to see if it changes. So we can test this now. And we're gonna test it as our manipulator moves, so that we can see that. No, sorry, we can test it for this point of the inverse kinematics, because the inverse kinematics we're solving prior to the visualization. So I'm gonna put a breakpoint here, and then let me stop what's running. And now let me run the debugger. So this is gonna bring me back. No, it's better if I run it entirely. Sorry, because I want to see the values printed. And if we go back, then if you see here, it converged on this under the same number of iterations as the previous one. This is mainly because this problem, it was very well initialized, and also the gamma that we're choosing is it's 1. So let's try reducing our gamma here to 0.5. And then let's stop it, and then we launch it. And then we go back here. And then you see that the number of iterations it's larger. And this is because our alpha didn't like the length of the error, so it reduced the step. If you take shorter steps, then that means that you're gonna converge slower, but it means that you're gonna get to a more precise solution. And you might say that, why is this better? Why is reducing the step better? But this is clear when we have in the problem which is out of the workspace. So let's compare the two. So let's start with the one without the line search. So I'm just commenting out the line search algorithm. We deleted it. Okay. And then let's run our. So here, actually, I'm stopping after 10,000 iterations. And then after 10,000 iterations, it outputs whatever it's there, and tells you, okay, maximum number of iterations reached. There was no solution. I'm going to the closest solution that I found. So I selected 2.5 minus 0.2 is minus 0.5 pi, and the algorithm outputted this, which is very far, and the norm of the error is quite large. And let's take a look at the position of our manipulator now. And if we, just by looking at the X position, let's show the world frame. We need to add the axis. Let me add them. Okay, let me make them a bit smaller. A bit slimmer. Why didn't the radius change? Okay. Well, this is too small. No. Okay, this is better. So if we look at the X position that the inverse kinematics output, it's minus 0.14, and we're asking it to go to 2.5. So, I mean, you can already see that we are, so the X direction is the red axis, and you can already see that we're quite far from it. Now, let's try it with our line search algorithm here. And we stop it, and then we rerun it. So it's never going to find a solution because it's outside of the workspace, but then we'll see something that it's interesting. I should have saved that one. Let's show again our access. So it is not on 2.5, but you can already see that the total length of a robot will never reach 2.5 because it's about 1 meter. The length of the length is 0.5, but at least when we did the line search, it got closer to the solution. And maybe if we let it run for a longer time, it will get closer and closer, but it will never reach the solution, but at least will give us a better solution than just keeping our constant time step. So, and then we can see here that as the iterations progressed, it reduced. First, it took a step of 0.5, then 0.25, and then and then it reached it stopped here because the error was just becoming constant, and this is the final value of alpha that it found, and this was the one that provided the best solution. So this is just to make the point that it's worth doing the line search. Also, when the problem becomes harder to solve, so when you have like both prismatic rotational joints and many degrees of freedom, for example, like in a humanoid robot, where there are lots of redundancies, doing the line search is worth because you get it closer to the solution and you get a more accurate solution. Of course, it might take a bit longer because you're taking smaller steps. But something that we didn't see in the lecture, you can actually define the direction of the step. So you can compare the errors and find the correct direction of in which you need to go to get closer to the actual solution. Okay. So that's all for kinematics. So we're going to start with the part on dynamics. So let's look at our description. So in this part, we're going to implement the recursive Newton-Euler algorithm. And this is one of the two main algorithms that are used to solve rigid body chains and in robotics. The other one is the articulated body algorithm. And the description here only says that we're going to use Pinocchio, but we're actually going to write the function ourselves. And let me get my other PC here just to have it as a reference so that I can just write the code along with you. This is terribly slow. Okay, good. So now let's take a look at the equations of our recursive Newton-Euler algorithm. So remember that we have a forward pass and a backward pass in the recursion. So the forward pass, it's to compute the accelerations. So first, to compute the accelerations, we need to compute the velocities. And we have the velocity of the previous link, the angular velocity of the previous link, plus the joint velocity of the joint that we're computing. Its angular velocity and its z axis. Remember that it is the axis of motion of the joint. And here the professor indicated omega 0 and omega dot 0 because we're going to start from the base, and the base is not moving, so it doesn't have velocity and acceleration. And actually, the joint of the base is also not moving, so the angular velocity is going to be 0, and the angular acceleration it's going to be 0 as well. Then for the linear velocity, we have again the computation with respect to the previous link, and then we have the computation of the acceleration, which is just taken from the derivative of the velocity. And again, what's very important is just to keep tabs on the indices, because I talk from experience. When I was working out this function, I messed up the indices a lot of times, and it took me a lot of time to figure out that the error was on those indices. So this is the step for the acceleration. Then it is important that we need to compute not the acceleration with respect to the joint frame, but the acceleration with respect to this with the center of mass. So we need to repeat this last step with with respect to the center of mass, and we're going to get the information of where the center of mass is located from the URDF. Okay. Then for the backward recursion, we're going to start from so that the backward pass, we're going to start from the end effector. So for example, in a manipulator which is in free space, the forces and the moments at the end effector are 0. So it's easy to compute it from there to the very bottom, to the base frame. Of course, if you're in contact, you would need a force or a 6-axis sensor to detect the force and moments acting on the end effector to perform this pass, or estimate them as well. There are people that work a lot on estimation of forward and contacts in general. So for the forces, it's easy because this I+1, it's basically if we start from the end effector, this is 0, and then this is mass time acceleration. What's important to note is that and I forgot to mention that for link 0, the acceleration is just going to be the gravity, and this is because it's not moving. And this makes our computation easier, because when you move through the chain, you're just taking the acceleration with respect to the predecessor link. So if gravity is considering the base link, then we don't have to perform transformations of the vector of gravity in the frame of the joint along the entire kinematic chain. So this is very important, and it's very important that we do it here. Otherwise, we would have to get the gravity at this frame and then transform it to its reference. So apply the rotation matrix of the gravity vector expressed in the frame of the joint. Then for the moments, again, we have this expression, and then we compute just basically the lever arms with respect to the center of mass, with respect to with the center of mass of the predecessor joint and the next joint. So these are the lever arms, and then these are just the centrifugal and Coriolis, what generates the centrifugal and Coriolis terms, which are just related to the angular velocity. So the moments related to the angular acceleration and the angular velocity of the joint. And in the end, we're going to compute the moments and forces. So in our case, we're only going to compute this bottom part. Actually, these expressions are only for revolute joints. So we're only going to compute this bottom expression. So, okay, let's get to work. So if you have the file that I provided, here we're going to implement our recursive Newton-Euler algorithm. So first we need to know what we need. And to our parameters, we need to add the location of the center of mass for each of the joints. So let me go to actually the first function, which is the set over parameters function. And then what we're going to do is we're going to set the location of the center of mass with respect to its joint frame. So we'll do it like this, NP array. And then, for example, for the first link, we have it at 0.0,0. Then so that's the base frame, and its center of mass, it's located at the origin of the joint frame of itself. Then for the second link, which is the short, so the second one is actually the same. It's actually located at the origin of the joint frame. Then the third joint, it's actually a bit this. Well, the second joint, sorry, it's actually displaced by 0.28 meters, and so this is 28 centimeters. We could actually take a look at the URDF and see where this is. So so our URDF, it's in the folder. So if you go to the locusing folder, then there's our folder L3 Kinematics and Dynamics, and then we have another folder called Visualize UR, and then we have UR4. Then you have UR4 description, and then the file that we're looking for is UR4_robot URDF. So let's look for the link that we want to see. So the base frame is here. Is this the base link? Let's see. Yes, this is the base link. So here's the indication of the base link. It's line 65. And then we see that the origin is located at 000 with no roll pitch in yaw. Okay. So now let's go to the second one. It's the shoulder link at line 102. And again, this one is a 00000 at 000. And then the upper arm link is where it has it's displaced 0.28 meters, so 28 centimeters. And this is where we get the information. Okay. So let's go back to our parameters. So I'm just going, so the other one that has its center of mass displaced is the second one. Sorry, the joint 3. And then for the others, they are all at the center of mass. Let me put on my glasses because I'm getting lost. So the other one is just basically the last joint. And then we want to output this. Maybe if you didn't pull from the latest version, you also need to add the tensor of inertia of the base link. So this is the tensor of inertia of the base link. Yeah, so if you didn't pull, you can copy this value from the URDF. So again, I can show you the URDF. Shoulder link. Yes. So this is where the tensor of inertia value. So these are the values of the diagonal. Remember that the tensor of inertia, it's expressed with respect to the COM frame. Then we already have the tensors of inertia, the masses, the mass of the base frame as well. I don't remember if I put it in the previous version. So let's add. Let me see the value that I use for this one. Just that I can. So COMs. So let's make our COMs vector, which is basically COMs equals MP array. And then mass. Oh no, actually, no, it's COM 0, comma, COM 1, comma, COM 2, comma, COM 3, comma, COM 4. Okay. And yes, this is the output of this, the last output of our parameters. So let's then go to our recursive Newton-Euler algorithm function. Yes, which is in line 330 approximately. If you haven't, if you're, it's approximately, probably you you use a different one, or you're jumping lines differently than I am. So let me just go to my, too much. Okay, so let's define this. So now I have tensors, but I also want to define the COMs. So there you have it. And then let's set this one. So let's put this prefix in the values of the inertia, just that we know, so that we know that these are the tensors of inertia with respect to the center of mass. So a trick that you can do, oh, this is not what I wanted to do. Is this the one? No, that's not working. No, anyhow, let's do it the old-fashioned way. So I'm just adding C just to be sure that these are the tensors with respect to the center of mass. Then I also want to get the masses. So mass 0 is M 0. Then I'm just gonna copy this multiple times. So mass 0, mass 1, mass 2, mass 3, mass 4, and 4, and 3, and 2, and 1. Okay. So we have the masses, the tensors of inertia, and the center, and we also want to set the center of mass of each of the links. So the center of mass are, so let me just see, yes. So COM 0 is COM 0. And then from here on. So these are the center of the position of the center of mass with respect to the joint frame. So just, I mean, with putting this C here, it's actually the joint frame. So again, let's do this. Let's do, oh. Okay. So we have our center of masses, and then here we're just initializing some variables. So here we're just taking the length of the vector Q, which is the vector of joint positions, just to see the number of joints that we have. Then here I'm just defining a vector 0, V, which is just to make the initialization easier. So I'm just plugging in this vector of 1 by 3 because this is something that I'm going to be using repeatedly in all of the vectors. You can also define an array, but just I didn't want to mess up with dimensions again. So I just you can just there's a specific shape that you can give to this one, and we could have created one of those for each of this, but it's the same. Now notice that our omega vector, it's should be, and this is something to be noted, should have 5 elements, because we're also considering the base frame. So we need to add, there's an extra parenthesis, sorry, an extra square bracket here. So we need to add an additional 0 vector to all of our Cartesian space variables of the velocities and the accelerations. So we have the velocities of the angular velocities, the linear velocities, the angular accelerations, the acceleration, and also the acceleration of the center of mass. Remember that last step that we were doing in the Newton-Euler algorithm? Then we need the acceleration. Now, prior to this, of course, our Q vector is of size 4, so we need to add the velocity of frame 0, which is basically 0. So frame 0, it's the base frame. So I'm just going to insert the value of 0 onto our Q vector. So I'm going to put it at the beginning. So this function insert basically puts select. You need to put the first argument. It's the array that you want to modify. The second argument, it's the index of the position where you want to insert the value. And the third argument, it's the value that you want to insert. So I did this for Q. Now, let me do it for QD and QDD. And then we do this and this. Well, just I forgot to mention that the inputs to our recursive Newton-Euler algorithm are going to be our vector of gravity, which is going to be 009.81, the joint positions, the joint velocities, the joint accelerations, and let's add what I mentioned before about having different forces and moments at the end effector. So we're going to add an extra argument here just to see this is the force at the end effector and this is the moment at the end effector. Okay, so we are adding these two extra arguments. Let me, even though if PyCharm doesn't like it, I'm going to just leave it without the spaces. Okay, so we have we had our extended vectors with the 0 joint velocity and acceleration at the first value, our initializations, and then we also need to initialize our forces and moments at each of the joints. Remember, we're going to compute the forces for each of the for each of the links, and so remember that the end effector doesn't have any velocity, it doesn't have any joint variable. So here I was computing it from joint 1, but actually we need to add an extra one because we're considering the base link as well. So here as well we need to add a 0 vector. So now we have the force at the base link, the force at the shoulder link, the force at the upper arm, the force at the forearm, the force at the wrist, and the force at the end effector. Okay, so that's why we have a vector of 6. And the output, it's going to be only the moments at, let me get if my computer decides to cooperate. Okay, there you go. The output is going to be we're calling it tau. Don't get confused. Sometimes tau it's used for joint torques, but now we're using it for generalized forces. So we are using the output is going to be the moments at each of the joints. So it's a vector of just so now we're initializing it just with a 4x1 vector. So now it is time to look back at our algorithm because we're gonna need. So one thing that we're gonna need, it's the position of the vector with respect to its predecessor length. Now, something that it's important to note is that all of our computations, we're gonna be doing them as we did in the lecture with respect to the world frame. And this is less efficient, but it's easier to understand. The most efficient one is when you do it with respect to actually the previous link. So you would need to add I think in the newest version of the slides, we're going to add this computation with the rotation matrix. But this is with respect to the world. Okay, and then that's what we're going to do. And this is very important because otherwise, because we need to convert all of our quantities with respect to the world. So let's start by just getting the direct kinematics of our robot. So we're going to do T01. Let's do it more efficiently. 1, 4, and then end effector. So this is 4, 3, 2, and this is equal to direct kinematics of Q link, okay, which is the name that we gave to our extended. No, actually, this is of Q. Sorry. Because this is solving the direct kinematics of our manipulator, and we already wrote this function. Okay, so let's just put a comment here that says these are the global homogeneous transformations, transformation matrices, and then we can now find the position of the links with respect to the world frame. Okay. All the base link actually, which is the same as the world. So this is, so for P, let's call our base frame P00. So this is just going to be basically located at 0, 0, 0. So you might have noticed that I'm adding a dot. Sometimes I put a dot when because remember that Python, it's an interpreted language. So this is just telling Python that this is a float. So if you would add 0, it wouldn't, sometimes it doesn't know that it's a float. Although 0 is not an integer, but it interprets it as an integer. So then let's get the position of link 1, which is basically the rightmost column of our homogeneous transformation matrix. I'm adding an extra set of parentheses. And then we can just use this. I'm just going to copy paste this to get the others. 1, 2, 3, 4, 5. So this is end effector 4, 3, 2, 1, and then 2, 3, 4, end effector. Okay, let me get rid of this because we're already doing this. Okay, and now we're also going to get the rotation matrices. So rotation matrices with respect to the world. So let's call this R00, and this is going to give us, I'm going to use the I function, which gives me an identity matrix of 3 by 3. In its argument, it's the dimension of the identity matrix. Well, yes, it's 3 by 3. Then we do R1, which is T01. Now it's 3, 3, 3. So this is choosing the top right block that represents the top left block that represents the rotation matrix. Then I'm just going to copy this for all of the joints. So this is R02, R03, R04, and then let's put this in the vector 4, 3, 2, E. So we have our rotation matrices, and now we need to get the positions of the center of mass with respect to the world. So the position of the center of mass of link 0, it's basically P00 plus our C0, C0, because this is the joint frame of the base. It's basically the world frame. Now let's get it from with respect to 1, which is P01 plus. Now these ones we need to convert, because remember that the values that we got are with respect to the center of mass of the joint. So we need to transform them, and then we need to do the multiplication of the rotation matrix that we just computed times CCOM 1. Okay, and then we want to repeat this for every 2, 3, 4, 5. Do I have an n effector center of mass? I don't think so, because we're considering it massless. Yes. So the nth effector frame, it's the same as it's the same as the position frame. Now the center, because the nth effector is massless in our case. So now let's do this. 3, 2, 2, 3, 4. Okay. Sorry? Oh, sorry. Thank you. Thank you for noticing. Great. Yes. Now we have the positions of the center of mass. Then. So we also need to transform. So let's put a comment here. Positions of the center of mass with respect to the worlds. Yeah, so something that I forgot to do is that it's easier to arrange these things because we're going to do recursions, and we want to arrange this in vectors. Well, let's do it at the end. I'll do it at the end because I'm already here. So now remember that we have the tensors of inertia expressed with respect to the center of mass. So we need to transform them to be expressed with respect to the world. So again, for I0, we have our
Excuse me.
Yes, tell me.
You wrote PC1 5 times.
Thank you. Thank you for noticing. PCE. Yes. Well noted. Okay, good. So again, we need to get our computation of the tensors of inertia with respect to the world. So basically what we want to do, remember that the transformation from I'm just going to write it here, from a matrix from a tensor of inertia, it's actually R. I'm just doing something that is not supposed to, but because the star is not the thing, but this is just to visualize the tensor of inertia times its transpose. Okay, so we need to do this here. So actually, this is two concatenated matrix products. So the first one, it's R. Is R00 defined actually? Yes, R00, it's defined here. So R00, comma I0, and then the output of this is going to be multiplied by R00 dot T. Okay, and then we can repeat this for all of our tensors of inertia. I'm going to delete this. 1, 2, 3, 4, 5. No, this is not needed. So 1, 2, 3, 4. Then 1, 0, 2, 0, 3, 0, 4. 1. Oh, this is C underscore. So let's copy this. Okay. Yes, 4, 3, 2, 1. 1, 2, 3, 4. Okay. So now we have our transformations for the tensors of inertia. So let's arrange all of our quantities in a vector because we're going to do our recursion. So the first quantity that we want to put, it's P, and we're going to do MP array. Okay, so then we put P00, comma P01, and then let's do it faster. Maybe I can even put comma. 1, 2, 3, 4, 5. So this is P0E, P04, P03, P02, and P01. Okay, then we have PC equals NP array. So this is our vector of positions of centers of mass. PC0, comma, PC1. And I'm gonna just be a bit more efficient. 2, 3, 4, 5. PCE, PC4, PC3, PC2. And then we also need a array of tensors of inertia, which is I0, comma, I1, and then I can just copy this. 2, 3, 4, 4, 3, 2, 1. Okay. So now we have all of our ingredients to compute the Newton-Euler, the recursive Newton-Euler algorithm. So let's start with the forward pass, which is basically computing the accelerations from joint 0 to 1 to the end effector. And then we're gonna start with a for loop from I in the range of n plus 1, because remember that n, it's the number of joints that we have, but we're adding an extra joint, which is the base frame, which is the number of links that we have, but we're adding an extra link, which is the base link, and this is why we add 1 to the recursion. Then okay, let me just get this to be able to read it. Okay, so first let's do the condition in the case of the base frame, because we don't have any velocity for the base frame. So let's just add a condition for the base link.
Excuse me.
Tell me.
You missed the slash in the P array.
Which slash? Sorry.
Line 407.
The underscore.
Ah, yes. Thank you. The underscore.
Yeah.
Thank you. Okay, good. Okay, so now we have this if condition in the case of frame 1. So we're gonna call this P underscore is equivalent to this vector here. So Pi minus 1 comma I, it's our P underscore. Okay, so let's just and then this is just P0, which actually we could just Pi because it's because we're at 0. And let's just add a comment here just to make it clear that this is Pi comma I plus 1. So this is the vector that goes from sorry, this is from I to I minus 1. Sorry. So from I minus 1 to I. Okay. Yes. Is this the case? Let me just check the equations. Yes. Yes, from I minus 1 to I. then, so the base frame doesn't have any velocity. So we say that it's still, so it's not moving. However, I mean, this is true for a manipulator, but for example, if you have a mobile robot, this is not true. Still. So for example, a legged robot cannot, the base frame is actually, in general, we consider the trunk of the robot as a base frame. So it's generally not still. Then, because of this condition, omega 0, it's equal to 0. Although this is a vector, but let's see. Python figures out that it's a vector. V0 omega dot equals 0. So this is, I'm just putting the values now. What's important from this condition, that this is why we need a condition, it's because A0, it's actually what we mentioned about it being G minus G0, okay? If we go back to the equations, actually, if we, in our equations of motion, here you see that the angular velocity, the angular acceleration of the previous link, of course, is 0, 0, 0, and then the only acceleration at which is subject the base, it's the gravity. So that's why we put it here, and also this simplifies our life because you don't have to compute the transformation when you're doing the backward pass for the forces. So let's just put it here. Okay, then let's add our else. Let's see if, yes, okay. Now let's define the actual value of P. So this is, as we mentioned, the vector Pi minus Pi minus 1. So we need to also to put this condition at the beginning, because if we try this without putting the previous condition, then it will throw an error, the code while running. Then our second value, remember, well, our velocity, we're going to compute according to this equation. So we need the velocity, the angular velocity of the previous link times the joint velocity times its axis of rotation. Okay, so this is omega I minus 1 plus QD. Remember that we reformulated this vector link I times set I. Here we're doing matrix multiplication, vector multiplication with a star. Oh, yes, with a star. Well, I mean, in my computer it works, so probably it's correct. So let's see. Then for omega dot, what we want to do is do this equation. So again, we need the angular velocity of the predecessor link, the acceleration of the joint times the axis of rotation, the velocity of the joint times the velocity, the cross product of the velocity of the predecessor times the joint, the axis of rotation. So let's just write this down. This is omega dot this is I minus 1, which is a predecessor link, QDD link, which is the acceleration of the link, times set, okay, set I, plus the velocity of the link times the cross NP, the cross product of omega I minus 1. Sorry if the autocompletion is messing the. Now let me move this a bit. Okay, now you can see it better. Omega I minus 1 cross set I. Okay. Then let's continue with the next equations, the velocity. So the velocity is basically the velocity of the predecessor link, I minus 1, plus the cross product of NP cross omega I minus 1 cross this P underscore, which is, remember, the vector in between links, the vector that connects the link frames. And then this is our expression for the velocity. Now our expression for the acceleration is AI. So the acceleration of the predecessor link plus NP cross omega dot I minus 1 comma P underscore plus NP cross omega I minus 1 comma the cross product. Let's just, as a reminder, it's this omega I minus 1 cross the cross product of this, what we see here. Okay, so this is this. So this is omega, and I'll move it a little further, I minus 1 comma P underscore. Okay, so we have the acceleration. Now what we need to do, it's the acceleration of the center of mass, and basically we need to do the same thing as we did for the final acceleration, but now considering the displacement to the center of mass. So we have our AC vector here, ACI, and this is equal to, I got lost. Oh no, sorry, first we need to define actually the vector from the joint frame to the center of mass frame. So this is PC underscore PCI. Remember that we had our PC vector minus PI. Then now that we have this, we compute the velocity of the center of mass, which is equal to VI plus MP cross omega I minus, no, I, because we're doing with respect to the previous, which is I, P underscore, and then the acceleration is ACI, it's equal to the acceleration of I plus, so I'm just going to copy this, and then I'm just going to replace the indices. So this is I, so the predecessor link, let's say it's just I, and actually I also need to change this to PC underscore, and that's it. Okay, good. So we have our forward pass. Now for the backward pass, yeah, for the backward pass, we're gonna compute the force, well, now we're going to compute moments. So let me just get a better view of this. No, too much. Okay. So we're going to compute moments from the end effector link to 1. Okay. So where am I? Yes. So for this one, we're going to set up a for loop going in the opposite direction, which goes to from n minus 1. And this is going to become a bit clear. Remember that, so this is this n minus 1? No, this is n, sorry. So from n to going in the backwards direction. So this is how you specify the step that you want to take. So we're going to take from n to in steps of -1 to, and you specify, let's say, the index after the last one that you want to see. So we're going to get to 0. So we specify the second argument needs to be -1. Missing a colon here. So once we have this, we compute our PC vector again, which is PI minus PCI, and then PC1. So just to remind to you, we need remember that the moments that we need are the counteracting moments of the between the joints. So it's so we need the position of the center of mass of link I, and the position of the center of mass of link I plus 1. So that's why I'm computing this. So this is of link I and this is of link I plus 1. So PC underscore 1 is P I plus 1 minus P PCI. Okay. Yes. And now let's compute the force. The force is fairly straightforward. It's this one. So it's so remember that our forces at the end effector are 0. So in our vector, that's why we had our vector of 6 elements of 6 vectors of force. So the last element is going to be 0. So for and then just to clarify, this is mass times acceleration of the predecessor link. So now we have all of the accelerations. So now we can use this to compute the forces of all of the previous links. Okay, so let's do this. So this is F I plus 1 plus mass I, which is the mass of link I, times this ACI. Not sure if I need this parenthesis here. Well, let's keep them, and then if in the end it works, then we'll try to remove them. And I equals. So here I'm going to. This is going to be a very long line. So if we recall this is a lot of terms. So I'm just going to start breaking it into separate lines. So this is. So if we look back at our expression, we have the moment of the last of the next link minus the cross product of the moment. Well, this is the moment of the predecessor link. This is the moment of the next link, and then these are the moments generated due to the angular velocities. So this is the moment of I plus 1. Then I'm gonna break this in a separate line. So to break this in a separate line, you add a backslash. And yes, I think this should work. I don't know why it didn't put me in the right position. So MP cross PC underscore FI. So this is a moment due to the predecessor link that we're subtracting. And then we add a backslash. Why is it taking me all the way there? I don't know. And then MP cross PC underscore 1 comma FI plus 1 plus MP dot I1. So this is basically computing the last terms of the expression. So let me show you here. I'm just computing these terms here, which is this is just a matrix multiplication. So here we have MP dot I. Well, let me remove this thing, and then omega dot do you think they locked us? No. Well, let's hope not. Omega dot I. Then sorry, I got a little distracted because the door made a sound, and hopefully we are not locked. We'll figure out next time. Just to give you a bit of context of what's happening in the lecture room. So this is I dot omega dot. Then we have MP matrix product of omega I comma MP dot I comma omega I. So let's verify this expression. So this is I times omega dot, I times omega dot, and then omega times I. Is this dot? This is cross. Yes, this is a cross product, not the dot product. So this is wrong. So this is cross. Okay. So this is omega I cross the tensor of inertia times the omega I. Okay. So we have our expression for the moment. So now we have both of our equations for the Newton-Euler recursion. So let's compute the torques by just adding an additional for loop, and tau I, it's equal to MP dot of set I plus 1. So remember that we don't care about the moment at the base frame. We care about the base link. We care about it at the rest of the links. And I plus 1. And then we have our return, which is basically the vector that contains the. I'm missing a column here. Okay. Yes, and which is basically the vector of moments at each of the links. Okay, so now that we have a function that is able to compute the recursive Newton-Euler algorithm, we can simulate the dynamics by computing the different terms of the dynamics equation. So let me show you just the dynamic equation, just to give you a bit of context. So this was in no, let's go to PDF, publish, and then we go to initial couplings. So
what we want to do, it's just compute M of Q. So the generalized inertia matrix, also called joint space inertia matrix, the vector of Coriolis and centrifugal terms, and the vector of gravity terms. And then, if you recall the lecture of the professor, we can compute this by setting certain values in the function to 0. So this is here. So let's start by computing the gravity terms. So I'm gonna move this a bit upwards here. So our vector of gravity terms, so the input is going to be our gravity vector, which is I'm just setting as G0, and then let's look at our expression. We only need the vector of gravity and the joint positions. What this is going to happen is that Q double dot D is going to get this term to be 0, and QD being 0 is going to make this to be 0. So let's compute it. So G is, so let's just define an array defining this to be a vector of zeros. Then also let's make QDD a vector of zeros. And then we compute our gravity using the function that we just used, like which is its arguments. Remember that the arguments of the function are G0, Q, QD, QDD, and the forces, which in our case are going to be 0. Okay, so again, let's go here. So this is wait 1 second, because here we could use as an input a vector or a scalar, but let's just use the vector to the function, which is going to be 0.00 minus 9.81. So this is Q, QD, and QDD, and this is going to compute the gravity terms. Okay, now let's compute our joint space inertia matrix, or also simply called mass matrix. I'm going to remove this because this is no longer the number of the exercise in the description. And let's see, remember, well, let's give a look to the thing. So to get the well, let's do it in the same order as it is in the lecture. So to get this, the vector of Coriolis and centrifugal terms, we need to set the gravity to 0 and the acceleration to 0, and then this will get we'll get this vector of Coriolis terms. Okay, so let's do this. So I'm gonna do it here. So let's define our functions get C, which arguments are going to be Q and QD. Okay. Now let me try to go a bit. Yes. Okay. And then this is so let's just set QDD to be our array. So basically just the same as this. Then 1 second. Okay, and then we can just basically use well, let's just define G0 here to be the same as there. Okay, and then our function would look like this. And we know that QDD is 0, and our vector of gravity is 0. And then we return C. Okay. Now so here I'm going to put compute vector of Coriolis terms. And now here, let's compute the mass matrix, which is the most involved one. So for this one, we actually need to know because we need to do a recursion. If you remember here, we can only get columns of the mass matrix. So we're going to get each of the columns based on the number of joints that we have. And we need to provide the, so zero gravity, the joint positions. Remember that the mass matrix only depends on joint positions, zero velocity, and our selector vector, which is going to be basically, if you remember, if you have the acceleration, then it's just basically selecting the column corresponding to that term of the mass matrix. So let's do it. So we first get the length, and we define the size of our mass matrix to be n by n. Then for I in range of n, we define our selection vector first. We initialize it with zeros. 0, 0, 0, 0. Then we say that E element I is equal to 1. And then we compute our recursive Newton-Euler Newton-Euler algorithm. And okay, let's again set our zero vector here. G0, Q, and then we can also set QD here to be 0, QD, EI. And then we return the mass matrix. Okay. So we have all of the terms of our dynamics equation. So what's next is we need to simulate our robot. And to do the simulation, we go to our main file. Did you get the chance to copy, or?
I think you didn't
Ah, you're right. You're completely right. So because I'm computing here tau, but this is actually, let me just see if I did it correctly here. Yeah, I mean, this is M. So 4, I equals tau. Okay, yeah, well noted. Okay, now let's compute our, let's go to our dynamics file. So to simulate our dynamics, we already have the kind of the skeleton of our file. And actually, one of the exercises that we need to do it's implement a forward Euler integration, because remember that we're simulating setting the values of the joint positions, but these joint positions need to be computed according to the joint accelerations and the joint velocities that are coming out from our simulation of the dynamics. So how are we going to do this? It's by let's go to the lectures, doing a forward Euler integration. So this is forward explicit Euler, but we're going to use the improved forward Euler, which is basically this. We're doing an integration. So remember, because we're already computing with the algorithm, the acceleration. So we're going to integrate acceleration, get back velocity, and then integrate again and get back position. And we're going to use this with these expressions to compute those. So first we're going to get velocity, and then we're going to get the position. Okay, so this is what's defining our time step, which is our current time which is initialized at 0, and our dt, which is in our config file here, which in this case it's 0.001. It's L3 underscore conf dot py. Okay, so here we want to implement our forward dynamics. So sorry, our Euler integration. So to do that, we do. I just want to make sure I don't make any mistake. Yes. So first we get the velocity, which is it's QD, which is equal to the current velocity that you have, plus, so this is just getting the update of the velocity, plus the acceleration times QDED times, sorry, the step time. Okay, and then we get our position, which is our current position plus QD times our dt plus 0.5 times our acceleration. So it's is this one, and so it's this. I'm taking out the 0.5 out of the equation. Maybe I can get it here. So let's do the square of the square of the step time. I'm missing a times here. Times QDD. Okay. This is our forward Euler integration. Then what we need to simulate the dynamics, it's get the acceleration. So let's go to our expression. So basically what we want to do, it's isolate Q double dot. Now our torques in the system now are 0. So basically what we just need to do is just move these terms to the other side of the equation and invert the joint space inertia matrix. Remember, so in general, when you compute an inversion, you need to be sure if there's a condition in which the inversion is not possible if you have a singular matrix. But for mechanical systems, the joint space inertia matrix, it's always invertible. So let's do that. I think I wrote it down somewhere actually. Yes, I think I wrote down that in the description of the lab, which I have here. Yes, so this is basically the expression that we need, which is the inverse of the mass matrix times this. Okay, so QDD is equal to, let me just make sure I'm not making a mistake, mass, okay, so we need to compute first our terms. So we compute them by, so this is just using Pinocchio. Let's comment it out for now. And so yeah, I'll talk about this later. QDD, and this is equal to the, okay, let's compute first the inverse of our matrix, which is MP linear algebra dot inf m. Now we have mm times no mm dot, I need to verify if actually the, from what I know, the star, I think it's not, because here it works because it's a scalar. Maybe in the other ones it works because it's a vector multiplication, so it's the same as a dot product, as the inner product. But I'm not sure. Okay, so QDD times, so in general, sometimes they define H as the matrix of a vector of nonlinear terms. And this is basically C plus G. Okay. Let me just verify something real quick, just to be sure that I'm. Well, I'll check it later. Okay, so this is MP, like the inverse times our torques, which are 0. Let's call them. Well, for now, let's just keep it like this. And then this is just minus our H matrix. Okay. So in theory, we have everything to simulate a robot falling. So hopefully we don't have any errors. So let's run this. You can do this by doing Control-Shift F10, but I know that some of you are not able to do it. So if it doesn't appear here, you can go to Edit Configurations, and here you select the file that you want to run. So the file is in script path, and then you select the one that you want. Well, it already exists because I already put it there, but it's here. So now let's try to run it. And there's a syntax error. I'm missing in. So we're missing in line 412. So let's try it again. Where is this? Oh, I'm missing this column. Okay. Okay, I'm not giving any arguments to the functions. I'm not. Yeah, the functions that are there, let's just get them properly set. So L3. So yeah, I'm not giving anything. So let's recall what are the arguments of G, G0, and Q. So G0, it's equal to MP array 0. Insert 0, 0, 0, minus 9.81 and Q. Okay, then for M, it's just Q, right? Yes. And for the Coriolis, it's Q and QD. Q and QD. Okay, let's see if this works. Again. I'm giving 6 arguments. Because I'm not setting the forces, so I need to put. So let me just check something real quick. Is this correct? I'm going to remove the arguments for now, just because it's the fastest thing to do. And I'm actually not using them. Set robot parameters. It's giving me problems now because I am not 1, 2, 3, 4, and I have 1, 2, 3. Okay. Because the previous function and in the previous exercise we had the only one argument there. Yeah. Okay. Again.
If you see in the right corner, there are all the programs highlighted.
In the right
corner.
Yeah.
There are 5 red dot.
Okay. So line 4 here, undefined reference set. Oh, because I never defined this. Oh, actually, I'm missing defining the set vector, which I'm using there. And this is obtained with the Jacobian. Yes. Yes, comma z 1, comma set 2, set 3, set 4 equals compute and the vector Jacobian. Then actually we don't need the Jacobian itself. And then we need sorry, again, let me just check. Yes, we need set. It's an array, which is NP array. And then remember that the first one is an array of zeros, comma 0, comma 0. Oh, sorry, this is the three-dimensional vector. And then we do set 1, set 2, set 3, set 4. Let me just verify this, okay? Then this one, 434, it says that it's an unresolved reference. Oh, because I'd never initialized this, I think. Am I actually using it? I think I never used it. No. So this one we're not using, so I'm gonna comment it out. And it seems that we have no errors, hopefully. Not an error. Oh, because I forgot, I have a mistake in the. Yes. Why is this an error? Sorry. Okay. Okay. Why is this giving me an error here? Omega dot operands cannot broadcast with shapes 5 to 3. So omega dot. Which one is giving me? Is it the crossbar the one that's giving me problems? Shouldn't be. Let me just copy this specific line from the file that I already have solved. So let me. Okay. Base controller. Details. Changing details. This is the line that is causing me problems. But hopefully there's an error in the operands here. No. Didn't copy this one. No, it's not copying it. So let me just verify it by just looking at it. So what is the error here? Omega underscore dot I. So which one is the one that's causing me problems? Let's split it in two. Omega dot underscore. No, I cannot do this. So I'm gonna do this times 0. Well, this is not doing anything. So probably probably the only option that it's giving me problem is this cross product. And it's because of the set I, most likely. So set I is that should be this thing. Just let me look at how I defined it here before. So let me just get it from my previous file. I know. So this is a completely different definition. Zeros 1/3. Okay. Let's hope there are no more errors. No, the same error. Oh, okay, this is a different one. Oh, but I had, yeah. Well, I don't want to spend much more time looking for typos, so I just want to make you see what the file actually does. I'm going to push the correct one to the repo, and then just you'll have all the solutions already. So this one runs the dynamics. So what you're supposed to see, let me do it from the point at which we stayed. Here. Okay. So actually, we're adding damping. So let's first simulate it without the damping and see what happens. And for this one, I'm gonna not put a slow factor. Okay, so let's try to simulate it. And you see the robot falling now, but you see that it will actually never stop moving, mainly because a double inverted pendulum, it's a chaotic system. So without friction, of course. So it will just keep on moving without without ever stopping and without like following a specific trajectory. So this is what you should see when you finished implementing the algorithm. Then let me just kill it. I'm just gonna kill it now. Now let's add a bit of damping. So to add the damping, remember that we had the torque. So the damping that we're using now, it's basically a damping coefficient times the velocity of the joint. So we're adding damping for each of the joints, and we're multiplying it by this. And this is a bit of a high damping, but it's kind of realistic because an actuator has gearboxes and things like that. Yeah, let's run it. And then you see that it's falling a bit slower. And then it will come to a full stop when it reaches the bottom. Now, a final thing that I would like to do is to compare the results. So run it with Pinocchio. So I'm gonna comment out the functions that we just developed. This is something different. We don't need this. And now Pinocchio provides what I mentioned, the vector of nonlinear terms that includes Coriolis and centrifugal terms. So we're gonna do it like this, and then we're gonna do with H here. And let's see what happens. So it does the same, but you can notice that it is a bit faster than our implementation. And there are two main reasons about it, for it. One is that Pinocchio is implemented. So what we're doing in Python is just a binding of a library written in C++. So it is much faster. And the second thing is that we computed our dynamics based on the recursive algorithm we did it with respect to the world frame. But it's much more efficient to do it frame by frame and then perform the rotations at the end, because just by looking at the inertia matrices, it's full of zeros. So actually, when you have zeros, the computation is faster because it's sparser, and then a solver, let's say a good code, doesn't do the operations that have zeros. Like it sees a zero, it knows how many zeros it has, and then it doesn't do the operation. So you're saving computational time on there. And then when you're computing long kinematic chains, this is very useful. I'm gonna try to debug the code that we wrote today, and I'm gonna push the one that we did today. So this is the end of the lab session. Tomorrow I will start with the joint space control. Tomorrow, Monday, I will start with joint space. I saw your faces. So if you don't have any questions, I'll see you on Monday. I wasn't able to update my version of the code with what I run that one. Okay, shall we do this outside? We can do it now, and because they're gonna tell me to leave. I mean, it's really quick. I can fix it really quick, but we need to do it outside. Okay. Nobody else has questions? Good. Then I'll see you on Monday.
Bye. Thank you.